On behalf of the Vice-Chancellor and Principal, Professor Nana Poku, it gives me a great pleasure to welcome you to the inaugural lecture of Professor Kingsley Onyebuchi Obodo. The Vice-Chancellor conveys his congratulations and best wishes to Professor Kingsley. The Registrar, Dr. Cleland, conveys her apologies and thanks Professor Kingsley for his contribution to the School of Agriculture and Science. I would like to acknowledge the following guests this afternoon: members of Council, members of the Executive, Management, members of Senate, our inaugurant this afternoon, Professor Kingsley Obodo, family and friends of Professor Obodo, academics, professional staff, students, alumni, and distinguished guests. A special welcome to our guests from universities and organizations within South Africa, the African continent, and across the globe. Just to give you a background of inaugural lecture, inaugural lectures form part of the university public lecture series and may only be presented by newly appointed full professors who have been appointed in academic schools and centers. Inaugural lectures present an opportunity for showcasing the exciting and groundbreaking research and teaching being carried out by professors in our university. Each lecture represents a significant milestone in an academic career, providing official recognition of their promotion or appointment to full professorship. These lectures are furthermore an ideal opportunity for new professors to introduce themselves and to present an overview of their own contribution in their field to academic peers, student research collaborators. Inaugural lectures are also a platform for celebrating a professor's academic achievements with his or her family, friends, mentors, and colleagues. Distinguished guests, it is my pleasure to now introduce the Dean and Head of School of Agriculture and Science, Professor Ademola Olaniran, who will now formally introduce inaugural Professor Kingsley Onyebuchi Obodo.
Good evening. It is with great honor that I introduce our inaugurant for this afternoon, Professor Kingsley Onyebuchi Obodo. Professor Obodo obtained his Bachelor of Technology honors degree with distinction in Physics and Electronics Technology from Nnamdi Azikiwe University, Awka, Nigeria in 2007. In 2009, he received a master's degree in Material Science with distinction from the African University of Science and Technology, Abuja, Nigeria. He later on earned a PhD in Physics from the University of Pretoria, South Africa in 2014. Professor Obodo served as a part-time lecturer at the University of Pretoria from 2011 to 2014. He was a research scientist at Johnson Matthey Research, South Africa, between 2014 and 2016, and a senior researcher at the University of South Africa between 2016 and 2018. From 2019 to 2024, Professor Obodo worked as a senior researcher at the HYSA Infrastructure Center of Competence at the Northwest University, Potchefstroom, South Africa. He currently holds the position of Extraordinary Associate Professor at the Northwest University Center of Space Physics. He also serves as a visiting professor at the University of Nigeria, Nsukka. In January 2025, Professor Obodo was appointed as an adjunct professor at Addis Ababa University, Ethiopia. And on the 10th of February 2025, he joined the University of KwaZulu-Natal as a full professor in the discipline of physics at the School of Agriculture and Science in the College of Agric Engineering and Science. His research focus is on computational condensed matter physics with an emphasis on ab initio modeling, density functional theory, machine learning, and IEEE screening. His work spans hydrogen energy materials and catalysis, particularly liquid organic hydrogen carriers, water splitting catalysts, space-grade materials, 2D materials, spintronics, and related areas. His studies in nanomaterials encompass a range of physical properties, electronic, optical, magnetic, of systems such as MSINs, transition metal, dichalogenides, and graphene-based structures. Professor Obodo has published over 80 research articles in Scopus and ISI index journals, with approximately 1,344 citations, and he has an H index of 21 in Google Scholar. He has supervised numerous doctoral and master students and mentored several postdoctoral fellows across Africa. He is currently supervising multiple graduate students and has served as an examiner for several MSc and PhD theses at African and international institutions. He serves as a reviewer for more than 20 high-impact journals such as Nature, Applied Survey Science, RSC Advances, and so on. And he has also acted as guest editor for several special issues of journals. Deeply committed to teaching, Professor Obodo has held teaching positions at the University of Pretoria, the University of Nigeria Nsukka, and Addis Ababa University, among others. He has been an invited speaker at numerous international conferences and workshops in the UK, Rwanda, Nigeria, Ethiopia, Singapore, South Africa, and more. He has also given talks at various South African institutions, including the University of Pretoria, UNISA, and the Northwest University. He has organized or co-led several workshops and schools, such as the NITEX Quantum Espresso Mini School in May 2022, the first International Congress on Advanced Computational Modeling of Materials in 2022 at the University of Pretoria. Professor Obodo has received numerous funding awards, including Northwest University Research Support, HPC Europa Free Transnational Access Program for research visit to the UK, Access Managed Intra-Africa Research Funding, Knowledge Interchange and Collaboration Mobility Grant from the NRF, Unilever Science Communication Scholarship for UK travel, travel grant from the University of Pretoria, and the American Physical Society for Research visit to SLAC, Stanford in the United States. Professor Obodo has been a visiting researcher at several prestigious institutions, including the Stanford Linear Accelerator Center, USA, the Indian Institute of Science, India, the Institute of High Performance Computing, Singapore, King's College London in the UK, and the Johnson Matthey Technology Center, UK, among others. He is a C2 rated researcher by the National Research Foundation of South Africa. He served as a member of the 2024 Access Managed Initiative, an initiative affiliated with the African School of Electronic Structure, Methods, and Application. He has served as a resource person for the Integrated Vector Management Workshop organized by the African Union in Cape Town, South Africa. He also participated in the first US-Africa Frontiers of Science, Engineering, and Medicine Symposium in Nairobi, Kenya, and was appointed to the writing team of the African Union APET Experts Report on 3D printing technology. Professor Obodo is a member of the South African Institute of Physics, the Computational Science and Engineering Society of Ethiopia, and the National Institute of Theoretical and Computational Sciences, and so on. Congratulations, Professor Obodo, on your academic achievement. May I please invite you to present your inaugural lecture titled, Building the Future Atom by Atom, Computational Condensed Matter Physics for an African Renaissance.
Thank you. Thank you all very much for the very kind introduction. And I'll just start by showing my abstract, and just to give you an idea of what this lecture is all about. We'll be looking at reflection of my journey in Africa, particularly from Nigeria, and thinking about broader questions that we can answer. Why did Africa at some point stall in our materials development when we were kind of leaders? Why are we playing catch up right now? What are the necessary interventions that we should do to be able to address some of this? And this is a very personal journey for me. It started about 15 years ago. So my talk will try and talk about my background and give some overarching aim and the method that I've used so far. And the method that I've used, how it's have immense impact in our society today, which is the state functional theory, and also how we keep hearing machine learning and AI, and how it's shaping the landscape of material science and almost every discipline. And I'll focus broadly on some applications and on some study we've done in 2D systems and 3D systems. And then we'll try and talk about how condensed matter physics can act as a catalyst for African Renaissance. I am originally from Nigeria. I'll give a clearer picture, but just to give you a perspective of the distance, and this is why we talk about Africa is a very big continent. This is about 6,800 kilometers from Enugu all the way to Pietermaritzburg. And this is a very beautiful building here in Pietermaritzburg. Just gives you that Africa, we've got a very beautiful climate, and I'll motivate and I'll show you some of these things to tell you that we live in a very beautiful continent. And because of this, I think this can be some of the fundamental reasons why our materials development stalled. And if you think about, we are around the coast, the Indian Ocean. Now, some peculiar things you would find out that is not very peculiar in Africa is we do not suffer so much from earthquakes or some very devastating tsunami or things like that. And this is kind of some of the reasons I think affected our development. We were not suffering from a lot of situations that affected other Western countries that drove them to seriously develop. And going back to where I'm from in Nigeria, it's a very beautiful, hilly place. And this is somewhere around my village, which is Amantimolo in Eziagu local government area in Nigeria. We have a lot of coal in this part of the country, but considering the dynamics of Nigeria, this coal hasn't been mined for a long time. And part of the reason is because Nigeria as a country is deeply and richly blessed with oil. So we've got very fertile land. We've got a lot of things that would actually prevent us from developing further. The climatic condition there for most of the year is very warm and nice. And then you don't really need a jacket. It's hot. And so you ask yourself how much we build our houses and design things that take into cognizance these kind of unique climatic condition we have in Nigeria. And this is some of the motivation I think stalled our development. Now I'd like to show my parents here. So this is my mom and my dad, and they always say something, and I'm sure we understand what idioms are and the difference between idioms and proverbs. So I wouldn't go into the lexicon, but it says that if you want to eat a frog, you must eat the biggest frog. And part of this is that so that when people call you a frog eater, you will say, yes, I'm a real frog eater. And this has connotation in, if you think about the way Africa and materials relate to us today. We stopped because we were comfortable at our particular situation when it comes to our materials development. We felt we can outsource our development, and we stopped really developing. But the good thing is that there's a lot of change happening in the continent over a couple of years, and South Africa has been one of those countries that has been leading this charge. So just to go back, and I got some of these images from Wikipedia, you can see that the Igbo tradition, we had metallurgy, and very sophisticated metallurgy, making these complicated metal works back then. Now the question is, why didn't we take that jump from making these beautiful structures and being leaders today, maybe in 3D printing, becoming leaders in advanced manufacturing, leaders in advanced sculpturing, shape formation, materials rheology. It didn't happen because we felt comfortable, because we kind of solved a lot of our problems and we didn't have more problems to solve. But this is why this is important. Now we're going back and we're taking a step back. We kind of becoming more consumers of technology rather than developers of technology. And this is why we're rethinking, how can we do this? How can we translate our ancient knowledge into new sophisticated knowledge? I like this clay pot. It's a very good example of Asian African design with modern impact. Now, this I got from Amazon. So you can buy pots like this from Amazon. You can buy pots like this from Amazon. And this has got a top and it does a lot of things. So if you think about this previous pot, for all of us here, this is a scientific design, just thinking about it. It's made of clay that has porosity. And based on the porosity of the clay, we do not have, the water is cool because of the porosity, because of the structure of the clay pot. So you have cold water. And as well, the clay inside does not affect or does not affect the water quality or the water taste. So you get cold water, non-interacting, unlike today we have plastics purification. So this clay pot kind of solves a lot of those problems. And also it prevents bacteria from forming, which generally is a very good thing. So just thinking about this Asian African design that was previously my grandmother's house, but it's no longer there today. And today we've replaced almost all of these with more modern designs, so we say. But this served a lot of purpose. And I think this is part of the reason why our development stalled at some point. We designed one material that was able to take into cognizance that we needed cold water, acted as a barrier for lots of microbial growth, and also prevented and also did not interact with the water. But this is the idea that we need to think about Asian African designs and the modern impact it's having and how we can translate this knowledge towards better development in Africa particularly. So I wanted to look for something about KwaZulu-Natal, and I think you can all agree with me that KwaZulu-Natal, where our university is based, is a very beautiful province, very rich in culture, rich in terms of landscape. And something I would want to mention is, if you look at this building here, it's made up of thatched roof. And in the past, we had buildings like this made up of thatched roof, and we asked ourselves, why did we stop? And in some lapas, you would find thatched roof. And it served a lot of purpose. In summer, it made the place cool. In winter, it retained a lot of heat. And this is all materials. But fundamentally, understanding the individual steps of these materials and how we can actually just use them beyond the traditional sense is actually very important. And that's why we need to go back and say, okay, why did we stall? I think part of the reason why Africa stalled, like I've been motivating so far, is that we live in some of the most beautiful places in this world. We've got some of the nicest weather. And so in terms of going further to overdevelop, I think that's kind of a problem. And just wanted to show more pictures. And then for some of you that haven't been to KZN, and particularly Pietermaritzburg, this is where the Comrade Marathon starts and all the way to Durban. And so it provides you with a nice view and an appreciation of nature and understanding that there is a lot that this continent has to offer. And so the people in Africa particularly, I think we stalled a bit because we had almost everything. We have beautiful weather. We have very nice, gorgeous mountains that we can run around. And still in talking about modernity versus versus other part of the world. Now, this was my first time encountering snow, and I was quite old then, and this was Japan. I think this was in 2012, and this is Moses Mabhida Stadium. Now, this is kind of two contrasting images, but then you ask yourself, why am I having Japan and South Africa? I mean, we had a conference in this building, and if you think about this place, it was quite basic, but with all the modern amenities inside. And you can also see Moses Mabhida Stadium. This is an architectural wonder in South Africa. It's a very beautiful stadium, and it's next to the ocean. So it tells us that we can actually build stuff. But then, at what point are we just taking stuff and building things, or are we making the things we are using to build? So this is why understanding materials and making local solutions is kind of very important. And my next slide will speak to this. Now we live in a world where we hear about robotics and artificial intelligence. So I like this movie Terminator 2. It came out around 1991. And you can see back then, people thought about that we can have self-healing materials. And this is Terminator from the future, and then he can heal. And now in 2025, our robotics, and this is where we are now, it's still a very distant future from getting back to what the movie says versus what reality is. But the most important thing you can draw from here is that, where is Africa in terms of this kind of development? Where are we, apart from just thinking about robotics as code, there's also a lot of material science. If you look at the futures of the robot, there's so many materials that go into it, from the advanced electronics all the way to the materials that it's made up of. Now, all hope is not lost. I think maybe if you're listening to this presentation, you think all hope is lost. All hope is not lost in Africa. In Africa, if you think about our AI in terms of material science, in the West, it's mainly we have large labs. We are emerging, we're trying to develop, we're thinking about this in terms of infrastructure, where they are building shared infrastructure like Cyrus for us to use. In terms of research output, the research output it's not at the level of the global West, but we're starting to do some work in this area. In terms of innovation focus, in the West, you can see high-end materials discovery generative models. And then in Africa, we should think about African problems. And that's what I like about this, is looking at practical applications in key sectors. And I would like to mention that this slide, I got it all from ChatGPT. So I just asked this particular question and I wanted something, and then this is what it gave me. So the point I'm trying to make is that there is an area where Africa can play, and we don't necessarily have to start generating the whole big models, but we can actually start looking at practical solutions in key African sectors. And this slide also speaks to the previous slide, that Africa is not yet on par with Western countries in next generation material science powered by artificial intelligence and machine learning models. But we are actually vigorously making progress with our focus on real world impact, capacity building, and localized solution. And in the area, I will talk about the capacity building and localized solutions subsequently in my presentation. So being based at the UKZN, I'm asking myself, what are we doing at the UKZN? So I wanted something that looks, that tells us, that relates to African problem. So we will ask ourselves, how is 3D printed rocket components related to African problems? In Africa, we don't launch our own rockets. So we need to have one. China, there is. We outsource this. We don't have local competency. So it's kind of a good thing to see that in terms of this next generation materials development, the UKZN is actually trying to think around this scope, having a 3D printed rocket component lab. So talking generally now about the methods I've used, over the course of the years, I've used density functional theory and particularly computational modeling and done some experimental work. But the reason why I've mainly worked in the area of computational experimental design and modeling is because of the cost implication in trying to do experimental research, particularly in other part of Africa. South Africa provides a lot of infrastructure to other part of Africa, but particularly this is kind of a problem. And for us to develop, optimize, evaluate, and repeat the process towards novel materials for Africa, we need the cheapest cost solution. And I think starting with machine learning and computational design and computational experiments, it's a good way to go. And all of these, we can apply this kind of new thinking in development of new and advanced materials in energy storage systems, and actually creating solutions that change our fundamental understanding of processes in water and renewable energy, in pedagogical understanding. These are kind of important. And all of these can lead to an African Renaissance. So I have the computational method I've used largely is density functional theory. For the purpose of this lecture, I avoided most of the theories. And what we try to do here is to solve the many-body Schrodinger equation in terms of the Conshan equations. And this allows you to solve a very complicated problem instead of looking at all of the interactions, the electron-electron interactions. This is captured in terms of easily solvable problem of functionals. And this is the whole idea of using this powerful tool. Something we talk about is Africa, we need our own code. So in one of these, this is an area where Africa, we can develop our own code for African scientists. So in particular, all of these are not developed in Africa, and this is an area we can work together towards. And there are so many codes and so many approximations that can actually allow you to fundamentally study materials and understand the properties of materials. And before I exit this slide, one key thing about density functional theory is that you are able to describe material properties at the ground state level. So I talked about the method at a high level, and I said that let's treat this as a black box. Generally, what a lot of my students have done and what I've done in the past is you set appropriate parameters, so you do something smart at one end, and then based on this, you can interpret this your computational experiment and get something useful or sometimes not useful, depending whether you started with a proper parameterization of your system. So density functional theory and machine learning has a lot of impact in today's society. So we'll start from DFT. So the Nobel Prize in 1998 was awarded to Walter Kohn and John Pople. And this is for John Pople's case was for quantum chemistry, computational methods in quantum chemistry. And Walter Kohn was development of density functional theory. And if you check this paper by Walter Kohn and Walter Kohn and Sham, it's one of the most cited papers in science. Now, I'm thinking about machine learning, and a lot of my talk would not focus on this, but it's something that I would like to mention because it's something I'm really interested in, and it's the part I see forward for a lot of low-hanging fruit for African materials, reconnaissance, and research and development. So in 2024, the Nobel Prize was awarded to John H. Hopfield and Geoffrey Hilton. And this is for fundamental discoveries and inventions that enable machine learning with artificial neural networks. And also there is another Nobel Prize, and this is in 2024 in chemistry for computational protein design. What all this tells us is that even the Nobel community recognizes the power of developing novel theories and applying them to solve this kind of problems. So the next part of my talk would be a bit more focused on what I've done, and I hope you're motivated like I am about some of these things. So for this audience, I know I've got a lot of people from different places. So I started what's an atom. And from when I started school up till now, the definition of atom has actually changed. So now the correct definition is atoms can combine with other atoms to form molecules, but cannot be divided into smaller parts by ordinary chemical process. The reason is because we now know that we can split atoms, and we've been able to do that. But something that most people do not know is that most of the atom that you see is empty space. And atoms generally consist of 3 subatomic particles, which will be your protons, your neutrons, and your electrons. And the protons and the neutrons form the atom's central nucleus. And I decided to start with the hydrogen atom because the hydrogen atom is a more simpler kind of atom. So if you think about the hydrogen atom, the normal hydrogen atom that we have, you just have a proton and an electron revolving around it. There's no neutron. Then if you think about deuterium, we've got the proton and the neutron, and then the mass number is different. Then if you think about your tritium, this is a different kind of hydrogen. So in some instances, you might want to understand how atoms are made, and we all know we are made up of atoms and a lot of it. So if you think about it, this is now fundamentally, we as human beings, and we are also materials, we're made up of electrons and protons and neutrons. And if you think about the helium atom is similar, but now you have more protons and more electrons and more neutrons. And that's just what happens. So the heavier the atoms, the more electrons and the more the protons and the more the neutrons. So going from this now, you now understand what atoms are. And I want to motivate and tell you that if you think about atoms combine to give you a certain material, and this material has certain properties. So the way the materials are configured will determine the structure, and as well as it will have a structure property connection. So the way it configures will give it a certain property. And so based on this, I would stop at the crystalline and the non-crystalline, which is referred to as amorphous. There are quasi-crystals and a whole lot of domains now that we've discovered. But for the purpose of this lecture, and to keep it very understandable to all of the general audience, we know we'll look at the crystal structure. It's a depiction of the ordered arrangement of atoms, ions, or molecules in a crystalline material. So this will be a crystalline structure. This will be a crystal structure because it's arranged orderly. This is crystalline. And in the case of amorphous system, you have lack of long-range order. So long-range order is that at a certain distance, it's disorderly. But if you look at it from a localized point of view, you might have a certain kind of order. And this system is amorphous. And ordered structures occur based on the intrinsic nature of the constituent particles. And based on this, you can have different symmetries and different patterns and different dimensionality. So the idea of dimensionality is something I'll talk about subsequently. But before we go there, my first encounter of computational science started at African University of Science and Technology. And this was me then, and that's my elder brother. He's also a physicist. And this is me and him, and this is my elder brother as well. And this is a friend who is in the US in Intel right now. So back then, the first work I did, and this is based on a class project, was with Professor Umesh Wagner, and the whole of the class contributed towards this project. Where like silicon is a new material, and this is 2-dimensional silicon. Now, if you want to think about 2-dimensional, you have to think about like a tiny sheet of paper. That's an approximation for 2-dimensional, not necessarily, but to the first order. A 2-dimension is just a tiny 1-layer sheet, so it doesn't have dimensionality in the x-axis. And if you think about this was what we looked at. We were like, okay, can we evaluate silicon because graphene is a hot material that was recently discovered? And is this stable at first? How do we evaluate the stability? So to evaluate the stability of this material, we calculated the phonon frequencies. And if you look at the phonon frequency, the red line is silicon and the black line is graphene. In comparison to graphene, you can see that the phonon modes for silicon is actually lower than the phonon modes of graphene. And it tells us one thing. From just looking at this, it tells you that graphene is actually a harder and a stiffer material than silicon. And we've done a lot of work to show this, and a lot of people have worked on this. But something interesting that we looked at was we said, okay, can we introduce new atoms in this system? Like, can we dope this material? So in this case, we dope with chromium and see how this material behaves. So we studied a whole host of dopants. But one interesting thing is that we found out that doping this material with chromium results in a two-dimensional ferromagnet with a significant piezo-magnetic response. So you can see as you change as you apply pressure in this material, so this is the pressure we applied and this axis is strain, you can see that the net magnetization changes. It tells you that you can actually use this for systems that require piezo-magnet. So this tells us that this provided a basis for us to understand this kind of system and possibly get an application from this. The next part is, this is in 2011 when I joined University of Pretoria. So I started a project with, I met my PhD supervisor, Professor Neti Chetty, and he invited me over to South Africa. But we started working on this topic in boron nitride. And part of this was because previously I've already had an exposure to looking at two-dimensional material from my master's. And what we did then was, we were like, the question was, can we modify boron nitride? Boron nitride is a two-dimensional hexagonal boron nitride. And you can remember from previously, I explained what 2D is. It's just you take a three-dimensional boron nitride and you take one sheet of that. And interestingly, we evaluated the boron nitride and we're like, okay, it still has a large band gap. And the idea of the band gap is a material is defined as either semiconductor or insulator based on the band gap, whether if it has a band gap, a large band gap, or a small band gap, this will determine the property. And based on this, we are like, okay, can we further evaluate this system? So we now decided, okay, can we introduce a line of carbon inside there? So if you look at this black dots here, these are line of carbon. Interestingly, for this particular system, we looked at how the dipole changes across the junction. You can see the junction. You can see that there is a dipole change. The implication is that current can flow one side and not backward. And based on this implication, based on this, it gives us the basis that we can actually create a nano-sized electrical diode. And this is kind of important. And then if you think about a lot of smartphones and smart devices, you've got nano-sized components all lumped up into one. And this kind of this computational experiment gave us an avenue to explore this. In 2012, so I'm showing myself, this was me in Germany, and this is the triple point where you have Germany, I think it's Belgium and Netherlands. And this is my son, he was born in 2012, so now he's a big boy. So in 2012, particularly why I show that is, I started actively working on my PhD work, and I got the paper at some point in 2012. I thought I was never going to graduate because after the first year, I published in a different area, not necessarily related to my PhD. But the consequence of what I was doing in my PhD was we were trying to get a pedagogical understanding of protactinium dioxide. And sometimes people ask me, why this system? It was part of the fact that South Africa was interested then in pebble bed reactors. So we are like, okay, can we actually work on thorium and all this group of elements and understand this fundamentally? So using the existing theory as a then, we're not able to properly describe the system. So we applied different theories. And if you look at here, what we did was we said, we evaluated this material and we found out that it's elastically stable, it's dynamically stable. If I go back to my previous slide, I showed you what dynamic stability is, thinking about this in terms of the phonon frequency, and with no negative phonon modes, this is dynamically stable and is also energetically stable. With our approximation, we're able to get the reasonable band gap. Without the proper approximation, this is what we have. We're having this as sort of a metallic system. but naturally, this is not metallic. So we're able to properly evaluate and simulate this with proper approximation. So I'll jump towards, and this is in 2014. So officially I graduated, and part of what I did is what I showed you, and I want to motivate you why I did what I did for my PhD thesis. It was motivated first by the incomplete description of these actinide systems using conventional DFT approach because they are strongly correlated. And I also mentioned that these systems can be useful in nuclear generation, and they are quite expensive, so they have limited availability. So we can't just go and get nuclear materials and start working with them. And they're also very complicated. This is part of the reason why we looked at this. But some of the key findings from my PhD is that the use of DFT plus U-based method provides a rapid way to study strongly correlated systems, while other methods such as hybrid functional DW, DMFT plus DFT, etc., are computationally intensive. So, and the results that we obtained from the inclusion of this ad hoc parameter gave us a very good description of the systems of interest. So back to my roots in two-dimensional material. So in 2017, I was back with, I was at UNISA, and I was working with Professor Brown. I joined Professor Brown in 2016, and I was at UNISA. So we decided, okay, where is the easy point to start working? So I was like, okay, I'm interested in 2D materials, and we worked on different systems. But for these 2D materials, you can see the transition dichalcogenide and transition metal carbides and nitrides, which are magazines. So these are systems I worked on subsequently. I was asking myself one question: can we apply 2D materials as photocatalysts or photovoltaics, or use them in magnetic systems? But before you can do all of the calculations and try to apply this, you need to understand the fundamental theory of what a photocatalyst is. So a photocatalyst is a material that would allow for proton reduction to hydrogen and allows for water oxidation to O2. One material would do this when it's exposed to light. And so it means that it should be able to absorb sunlight and provide the energy required for the overall water splitting reaction. And why this group of materials, the transitional metal dichalcogenides and metal carbides and nitrides? The reason is because they are actually cheap. So it's cheaper to use these materials to do this. But generally, MOS2, WS2, and WSE2, which are transition metal dichalcogenides, have band gaps within the light absorption range. They generally have high photocatalytic activity. But something that they suffer from is that they have low stability and high recombination rate and low hole mobility. So when we talk about recombination, we're talking about that the electrons and the protons would combine. And so we don't want them to combine, we want them to be separated. And this is a problem. But also now I talked about the defining characteristics of photocatalysts. So now in the case of photovoltaics, what makes photovoltaics good? Photovoltaics, like you've all had, I'm sure you guys are very familiar, is that we want systems that can convert light into electric energy by harnessing the photovoltaic effect in semiconductor materials. And some of the challenges of, if you think about photovoltaics, is your land use, energy storage, variable power generation. And this is some of the problems that we have. But then something we can do about this is if we can improve the power conversion efficiency of our photovoltaics, then this can be very useful in terms of how we harvest sunlight. And some basic equation, I decide try not to put so much equation, is that our power conversion efficiency mu can be determined using this expression. So now going back to what we've done, we've looked at different MOS2 configuration. And I use the word configuration in the sense that you can stack one material on top of another material, and based on the different stacking, I can actually calculate, is this material feasible, will it form, and what is the optimal configuration of this material to form. And the reason why we do this stacking is because we can actually reduce the recombination rate of this system. And that's the major reason. We studied a lot of systems we've studied different configurations, and this is a work that is still ongoing, looking at different configurations to try and get systems that are good photocatalysts that satisfies the criteria I mentioned previously. So part of what we're still doing is band gap and band engineering, band edge position optimization via strain engineering. We're also looking at the maximum power conversion efficiency for these systems. And so you can see some of them are between the range of 7.2 to 12.1. Not very good, not very good, you can see. But the idea is we can get there. We can actually look at a host of configurations to try and improve the power conversion efficiency. So I would stop there and I'll talk about my time at HISA. And HISA at the Northwest University, so which means Hydrogen South Africa. So the point is, at this point, we are like interested in looking at hydrogen as an energy vector. And today, HISA has a refueling station for hydrogen. And this is me during COVID. So I looked for a picture that will be able to actually capture COVID and non-COVID and post-COVID. So this was at the height of COVID. I was going back to Nigeria, and this was just when the lockdown was lifted up, and then I was in the UK doing some research in battery-based system. And so this was just captures the dynamic that has been happening globally in South Africa as well. So in 2019, when I joined HISA, so I was like, okay, where should I start? Complicated. I mean, I don't know much about hydrogen or the hydrogen space, but I know a lot about MaxEN's 2D material. So I was like, okay, South Africa has a lot of platinum, and this is something that we want to use. This is something that we want to beneficiate, and this is part of the kind of research we want to do. How can I combine this? So what I did was I built heterostructures of platinum and MaxEN, and this resulted in my first publication while I was there. I would not go into so much detail about this. And part of what my time at HISA was quite successful, thinking about developing, getting a patent from experimental work and from theoretical work. I think this is kind of very rare. So we actually got a patent from some of this theoretical work we did on looking at how we can improve platinum using surface modifiers. So to give you an idea of what part of what I've done in between 2019 and 2024 is looking at liquid organic hydrogen carriers. So liquid organic hydrogen carriers are systems that can actually store hydrogen, and you can store hydrogen, and you can actually take it out you can actually take the hydrogen out via dehydrogenation, and you hydrate to store the hydrogen. And then why do we want to do this? Because we want to store excess hydrogen, and we want to ship our hydrogen, and then we want to take it out later. So what we need is and then it's actually a safe way of storing hydrogen, and you can store a lot of hydrogen. You don't need pressurization. You can store at different temperatures, low temperature, high temperature, depending on the organic carrier you use. And so I would not go into detail in this figure, but the important thing I would like to mention is that we have a dehydrogenation part and a hydrogenation part. The catalyst for hydrogenation is very cheap, so this is not an area that a lot of research is happening, but the dehydrogenation catalyst is mainly platinum and platinum group metal, which is kind of expensive. So we need to always improve the activity as well as the selectivity of this. So for a lot of work I did back then, I looked at toluene. So what we do here is that you can see we have hydrogen lean condition. You can see you have double bonds here. You can see hydrogen rich conditions. You don't have double bonds anymore. So we can take out the hydrogen, and you can store 6% hydrogen in each of these molecules, which is kind of good considering it's a small molecule. So, and I've showed you here, you can hydrogenate, add hydrogen, you can dehydrogenate, take out hydrogen, but we're more interested in the dehydrogenation part of this reaction. So what we've done generally here is to ask ourselves, how can we improve this catalyst? How can we improve platinum? So what we've added is surface modifiers, where I added different elements, silicon, sulfur, phosphorus, and tin. And these elements were not just selected in random, they were selected because they can poison the surface catalyst. So we asked ourselves, at what percentage of loading can we have that this catalyst is good? So we reduced our loading, and I'll go to the end and I'll show you the full dehydrogenation pathways, removal of the hydrogen here. And you can see for the different surface we considered, this is for the pristine surface, and then you have the different surface modifiers. And this is the pristine surface, and this is the surface, and then you have the modifiers. You can see generally for low concentration of modifiers, it's good. But as you increase the concentration of the modifiers, then you kind of have almost similar activity. So it tells us something that at low concentration, these our catalyst poisoners can actually act as catalytic enhancers and modify the surface of our catalyst. Another work we did lately, and this was part of an EU project, was to look at how we can form alloys. Now we've looked at small concentration of sulfur or different element. Can we form alloys of this? Can we use these alloys to actually improve the performance of this catalyst for dehydrogenation reaction? And all of this we are done using density functional theory as a computational experimental approach. The first thing is will all of these molecules actually stably absorb? We found that they will stably absorb on the surface. And in here, we look at the overall dehydrogenation energies, and you can find out that, and we see that our tin-based, our SN4PT actually resulted in significant improvement in the overall dehydrogenation energy. Actually, there's a significant drop. An important thing, the implication is that this can actually be a good catalyst for this kind of reaction. So this was my last day at HISA, and I was really excited and happy because of the future challenges. And I felt that HISA, I was very productive at that point in my career at the Northwest University. So I would not go into details because I've explained all of this to you. But then I will come to the last part of my talk, and this is computational condensed matter physics for an African Renaissance. And my wife sends me this picture of my two daughters in a box. And I feel like this is the approach that science should be. Science should not necessarily be a clustered approach, but different approach should happen. So what I'm interested in is building the next, if you think about African Renaissance competition, we need to think about how we can build capacity in Africa and especially research infrastructure. So the idea of mentorship, HCD development, human capital development is something that is very dear. Building new partnership and regional hubs, like creating like in KwaZulu-Natal, we should create new hubs in here. I think this is something that South Africa is quite good at, is developing a strategic African roadmap. And HISA was part of, HISA was a consequence of a roadmap of hydrogen roadmap that the government developed. And so we should, within this our roadmaps, ingrain innovation, inclusion, and entrepreneurship. And I think part of what I also think about is that we should think about application of scientific rigor and excellence in African research. African problems, we can look at our problems, and we can apply ancient knowledge to solve modern problems. And I think something that is very key in research is we should learn to develop partnership with different funders, both local and international, to address big scientific questions. I am actually, as I'm presenting today, we actually have a conference that started today, a machine learning methods for material science workshop. I'm organizing this workshop in partnership with my colleagues at the Northwest University. So the idea of this is that we should always think about capacity building in Africa and research infrastructure. And I think I'm particularly excited about the future in terms of machine learning and artificial intelligence, as well as integrating it to our existing knowledge framework like density functional theory, like experimental design and experimentation. And last but not the least, I'd like to acknowledge, I've got a lot of collaborators, and I'm sure some people are not here, but I have some colleagues here at the UKZN that we're working with, and we are supervising students with, like Dr. Anek and Upon. My elder brother, I've worked with him a lot, Joshua Obodo. He's also going to be part of the conference I'm organizing. And I'd like to thank my son and my daughter. This was me in Nigeria attending my younger brother's wedding with my mom here. And this is my beautiful wife and my very troublesome daughter, very active, and my adopted son here. And last but not the least, my daughter, very inquisitive. And then I tried to get pictures to be able to show some of the people that shaped my life. This is my immediate younger sister, and then she's older than this. So we are like 8 children, and I'd like to thank them for all of their guidance and all of their inspiration. And my brothers here, and then the last one of the family as well. And I'd want to appreciate the UKZN for this opportunity to continue to develop my career, for Northwest University, University of Pretoria, and UNISA for providing this platform. And yeah, thank you.
Thank you so much, Prof. Kingsley Obodo, for a wonderful presentation. I think all of us here who are listening to your talk will agree that we got a professor of a good caliber. And once again, congratulations. On behalf of the Vice Chancellor, Professor Napoku, the Chair of Senate, and the University Executive Management, we would like to congratulate you. One of the fundamental things that we studied around was around Africa and its goodness, and the African Renaissance in computational material science, as we concluded. One of the fundamental principles of the whole project renewal and the school of reorganizations, I think your dean, Professor Ade Olarin, will agree with me that we got a candidate, the incumbent of a good caliber of standing in a discipline. And we are proud of you to join University of KwaZulu-Natal. And we are of the view that your contribution to the university will make a mark, indelible mark into the university. And on behalf of the university community, we hope that you will be able to strengthen the disciplines of where you are. And we are so proud to make this decision for you to join the University of KwaZulu-Natal, and we're proud of you. Again, we're so proud that you managed to get even some compounds. I've learned something about actinide compounds and photovoltaic aspects of it. And it looks like I'm a backdoor learner here today. And we are hoping that you will still contribute more in terms of contributing, making more patents in the area so that at least Africa is in the right space. Once again, congratulations, and we're proud of you. Go and enjoy and celebrate this achievement today. Thank you very much.